Let's see how y'all did based on what we did yesterday. To prove that, what's the first step? Yeah, draw the line down the middle. That's straight enough. To prevent you from cross-contaminating, right? The left side and the right side have to be work as independent expressions. The goal is to make one side look like the other side, right? But for maybe font and color differences. So you want to start on the left side and try to build up the cosine into some kind of fraction. Ooh, man, did anyone bring a fraction machine with them today? Evan? No? Yeah. Let's start on the right-hand side, though. Then, I guess, not though, but then, that's the better word. And do what? We can chant, right? Okay, let's chant. Tear that down. Ready? 1, 2, 3. Tear that down. Yeah, okay. That was great. Yeah. Yeah, it's like the Berlin Wall, right? So we're going to do that. So we come over to this side because there's more information, and we're going to now replace secant with its definition in terms of x, y, and r, which is r over x. Good. Now, yesterday we did state change flip, which is perfectly fine. I'm just going to show you the other option. On the next line, not on that line, I'm going to multiply by the LCM over the LCM. Okay, we don't have to write the reasons, remember, but if there would be a reason for something, we would show it on another line. If you still want to do state change flip, that's fine. The reason this would be is identity element multiplication. We're essentially multiplying by a clever form of 1. If you multiply straight across, you get x times 1. And in the denominator, the x's divide out, not cancel. Someone said cancel last period. I cringed. Oh, yeah, my concussion came back. Ooh. And the x's divided out, and I'm left with r. Okay? And so now we have x over r, which, hey, we recognize that as the definition of which trig function? Cosine. So we have cosine of theta. And we look on the left, and we have cosine of theta. We look on the right, we have cosine of theta. And they're both purple. That's a bonus. Right? They don't have to be the same color. And so let me extend that line down. We have completed the proof. Okay? We have shown that cosine is, in fact, 1 over secant. And we have created this logical loop of statements that we can really jump in on anywhere and go clockwise or counterclockwise and show that all of these things are equal. Okay? Pretty cool. So remember, when you're done, and only when you're done, you get the privilege of signing off with something, right? Like this. Right? Man, that came so close last night. 2 chances at the end of regulation, and then it just didn't happen for him. Yeah. So Recum would be, yes, sports, which is the better of the 2 tech mottos to use. Because the other one would be this one, which I wrote this last period, and someone said, can you read that to me? Yeah, I don't read cursive. And I'm like, what? What is that letter? That's a G. Guns up, right? Guns up is not really the best thing to sign off with at a school, okay? So, yeah, even though that's their motto, right? You know, maybe they'll change it to like guns down, or down with guns, right? Let's wreck them, tear it down, but without guns, without violence. You can sign off. You could sign off with your name. I saw that. I saw someone doing that. Yeah, I saw someone doing that. I won't tell you who I saw doing that, but that's, you could sign off like that. I told you yesterday that my favorite, yes, is this. And sometimes when I dot my I, I put a little flame on there. Oh! Sizzle. Right? You almost had to say that at the beginning. Sizzle. So whatever you want. All right? Whatever you want. Just keep it clean, right? I said yesterday, don't put like F yeah or whatever. Monosodium glutamate, that's not really good either. That's unhealthy, MSG. Function? Function, yeah. Yeah, as long as you put a comma in between there. Okay, so there you go. Any other comments or questions? Now, that is That is not an easy word to spell unless you know a little bit about the German language, right? Because prior to becoming that spelling, it was originally just this, right? Wünsch. It's the umlaut U, which is how is it, Mark? Well, that's the Americanized UE without the umlaut. I'm asking you, with the umlaut, how would you pronounce it in German? There you go. Louder. Wünsch. There you go. The U umlaut is U. Yeah, yeah. And thank you, Mark. That's good. So when you have a German word with an umlaut, you drop the umlaut and add an E after it, right? There you go. You knew that, right, Caroline? Yeah. Mm-hmm. And also, Caroline, if you drop the I, becomes Caroline. Caroline. So that's Caroline Winch. Sizzle. All right. So whatever you want to do. All right. So let us go ahead and learn another set of identities. We've learned the reciprocal identities, but when I say we've learned them, that's not entirely true, right? We reviewed them because you already knew those. Same thing with this next set. I call them the quotient or the ratio identities. Either one. I tend to lead towards ratio. Guess what, guys? You already know these also as well. You already know them. You already know them. Here it is. Tangent is equal to sine over cosine. Oops. Tangent is sine over cosine. Did y'all know that? You absolutely did. Because, yeah, if I ask you to find the tangent of an angle on the unit circle, you would find it by taking the sine value, the y value, right? Sine y. And you would divide it by the cosine value. Cosine x, right? Y over x, sine over cosine. Tangent is sine over cosine. That is the ratio identity, okay? Now, we're going to prove one of these, but once you have an identity, you're allowed to manipulate it. So, like, if you wanted to multiply both sides by cosine, you can create a new identity. You could say sine of theta is equal to cosine of theta times tangent. You can manipulate the identities. This is another identity. Do you want to remember then that sine is the same as cosine times tangent? You want to memorize that? Not really, because it is an immediate consequence of the fundamental identity. You can obtain it real easily from the fundamental identity by multiplying both sides by cosine. So we're not going to memorize that. Similarly, you could say that cosine is equal to sine over tangent. You want to memorize that? Not really, because it's a direct consequence of something we already know. Now look what else we could do. This is just playing around, right? I can use these other identities that we just reviewed, the reciprocal identities, and look what I could do. I can make replacements. Sine is the same as 1 over cosecant of theta. Cosine is the same as 1 over secant of theta. Stay, change, flip, and we get secant of theta over cosecant of theta. So tangent is also equal to secant over cosecant. You want to memorize that? Say no. No, why not? It's not fundamental, right? It is a direct consequence, easy to obtain with just a little bit of algebra from something that you've already memorized. Tangent is sine over cosine, okay? But it is true. That is an identity. Tangent is secant over cosecant. All right? So cotangent then is going to be what? X over y, also known as cosine over sine. So tangent is sine over cosine, and cotangent is cosine over sine. And you can do all the fun stuff with that one as well. But this is what we're going to memorize, okay? Now, let's prove it. Oh, before we prove it, the reciprocal and the ratio identities, because they're single factors, single terms, they work for any power. So, in other words, 1 over cosecant squared is the same as sine squared. All right? It doesn't always have to be just to the first power, because 1 over cosecant squared is 1 over cosecant times 1 over cosecant, which is sine times sine, or sine squared. Here's another kind of example. Tangent to the fifth. Well, tangent sine over cosine, tangent to the fifth is sine to the fifth over cosine to the fifth. They work for any powers, okay? Any powers. They don't have to be ones. All right, so let's prove it. I know you don't believe me. Cotangent is not cosine over sine. Right? All right, I'll prove it to you, Thomas. Doubting Thomas, right? Yeah. Oop, that almost violates separation of church and state. My bad. Okay, on which side shall we start? Should we start on the left and try and build it up into a quotient? Nah, let's tear that down. Okay, I did that one by myself. I need to be a little bit quicker to help on the chance. All right, so on the right-hand side, I'm going to replace cosine with its definition in terms of x, y, and r, which is x over r, all divided by sine of theta, which is y over r. The reason would be off to the side that we don't have to write definition of cosine and sine. You don't have to write the reasons, but if there is a reason, you need to show it. Now we have a complex fraction, so like, yay, yay. So what we essentially did was an identity replacement, except we did it with the definitions because it's fundamental. Once you do an identity replacement, then you're going to be looking to do some algebra, right? Cleaning up the expression. We have a complex fraction, so you're like, yay, the next step is to eradicate it. And we can do state change flip or lick them over lick them. It matters not to me. What do you want to do? State change flip. Okay, so on the next line, we're going to have x over r times the reciprocal r over y. And the reason would be state change flip or division algorithm. You want to put that? And now what happens to the r's? Don't say cancel. Don't say cancel. They divide out. Okay. And we're left with, and if you're going to divide them out, make sure I can still see that they were there, right? Because remember, the process is the product. You don't even have to divide these out. You can just leave it without showing the lines through it. And then we're left with x over y. And now you're like, x over y, x over y, x over y. That is the definition of cotangent. Now, let's say you get stuck. You're like, I'm stuck. I don't know what to do, x over y. If we're starting on the right-hand side, then the left-hand side becomes our what? Target. Yeah, that's my target. The side on which you are not working becomes your target. And so you have to work towards that. All right? And so that gives you some direction in which to move. Now, x over y, let's say you were stuck. You could jump to the other side and say, oh, cotangent, that's x over y. And that would also complete the proof, right? Because the bottom line on both sides, but for the color change, are the same. Okay? Now remember, it's preferred, although this is not wrong, it's preferred to do it all entirely on one side. It's kind of more of a challenge, which I know y'all are up for. So what you could do is if you have to do this, then remember, again, we've created this logical loop of steps that can go in any direction, right? Either way, arrows, 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 either direction. So this can give you insight on how to complete it on one step. Just say, oh, if that is here, then I go up, then this would just be cotangent of theta. And now I can get rid of it on that side, right? And now you have it on one side. So just kind of nicer, but not wrong if you do it the other way. And now we have cotangent of theta equals cotangent of theta. And then I put my sign off. Noise. Yeah, noise. What's that? The click? Oh, how do you spell that? Oh. No. Okay, how about I just put memes. Okay. There you go. Mimi. Or as she spells it next door. Yeah. Mimi. Mimi. Oh, that's almost what the Roadrunner said. It said beep beep. What? Yeah. Okay, so we've learned two sets of identities, the reciprocal and the ratio. And by learned, I mean reviewed. The only difference is that I have put them in a nice commemorative box for you, right? Suitable for framing. The next set of identities, unfortunately, are going to be probably new to y'all, unless you've been like reading ahead. These are called the Pythagorean identities. The Pythagorean identities, or as I love to call them, the PIDs. Okay? These are the PIDs. P for Pythagorean, I for eye, tooth for tooth, D for identities. Got it? PIDs. Now there's 3 of them. And you might say, why are they called the Pythagorean? Is it the same guy that didn't eat beans because he didn't like to fart because he thought it would lose part of his soul? Is it the same guy? And it's like, yes, it's that same guy. Cheese would be the antidote for beans. There you go. All right, nice. Bean and cheese taco. That's the perfect meal. Pythagorean identity. The first one, oh yeah, good point. This one I call Papa Pid. And that's Papa with 2 P's, not Papa with 1 P. It's more like Papa Murphy instead of Papa John, right? Papa John is like pervert, okay? Papa Pid is more like Papa Murphy. Papa Murphy is the new Prince of Pizza, okay? Not Papa John. Papa Murphy's. Well, Little Caesars doesn't start with Papa. Evan, you see what I'm doing here? Papa Little Caesars. I guess we could try to make that work. This is Papa Pid. Now, before you ask, no, there is no Mama Pid. He is a single father. Okay? He is a single father. I think they're working on making a Disney movie about him, where the mother always dies and is never there. This is another one of those cases. Okay? That's tragic. Have you noticed in Disney movies, where's the mother? Right. Okay. All right. So why is this Papa Pid? I'll show you. We're going to prove it on the next example. But notice it says cosine squared plus sine squared is equal to what? 1. They're one and the same. If you ever have the number 1, you can replace it with cosine squared plus sine squared, and it's equivalent. Okay. Now, does that mean that cosine of x plus sine of x also equals 1? No. I could take the square root of both sides. Square root of 1 is 1, but the square root of cosine squared plus sine squared is not cosine plus sine because these are terms, not factors. So they have to be squared before you add them together in order to equal 1. Now, here's what's cool. This is Papa Pid, but once it is an identity, and we'll prove it, you can manipulate it. So you can solve for cosine squared if you want by bringing the sine squared across, and you get 1 minus sine squared. This is what's going to show up a lot when we do proofs. You'll be looking at a cosine squared, and you're like, I'm going to replace it with 1 minus sine squared. Or vice versa. You'll be looking at 1 minus sine squared, and you'll be like, ooh, that's cosine squared, a la Papa Pid. Now, here's what's cool about calling it 1 minus sine squared. 1 minus sine squared is a difference of 2 perfect squares. So that would factor into 1 minus sine times 1 plus sine. Holy moly, smokers. We just invented a new identity. Cosine squared of x is the same as 1 minus sine times 1 plus sine. You want to memorize that? Say no. No, because it comes freely and easily by manipulating Papa Pid. Okay? Now, you can also solve this for sine squared if you want to. Sine squared is 1 minus cosine squared. Okay, and then you can do 1 minus cosine, 1 plus cosine. Pretty neat, right? Pretty neat. Yeah, I know. It's exhausting learning all this crazy new cool stuff. Now, that's Papa Pid. Okay? Now, there are 2 others, and these are his offspring. Okay? He's like the seahorse dad that gives birth to the baby seahorses. This one is called Baby Pid number 1. Baby Pid number 1. He's the older of the 2, okay? He's the older of the 2. He came out of the belly first, okay? So notice it's 1 plus tangent squared, again, squared, equaling secant squared. So not only memorize this, but realize that by this identity, you can relate tangent squared to secant squared and vice versa. Just like over here, you can relate cosine squared to sine squared and vice versa. Now, once you have this memorized, you can solve it for tangent squared if you want. Tangent squared of x would be secant squared of x minus 1. That's true. You could solve it for 1 if you want. 1 is equal to secant squared of x minus tangent squared of x. Once you prove that it's an identity, or you know that it is, you are allowed to manipulate it. Now, I wouldn't memorize those other two forms because, again, they come so easily. But look what we could do now. If 1 is equal to secant squared minus tangent squared, and 1 is equal to cosine squared plus sine squared, we can now say then that secant squared minus tangent squared equals cosine squared plus sine squared, right? You want to memorize that? No. You can also say then that 1 equals 1. You want to memorize that? Now let me show you why he's called baby PID number 1. You're like, okay, he's just another one. But yeah, baby would imply like he's like an offspring, like a result of. And yes, that is true. If you take Papa PID and by asexual reproduction, you divide everything through by cosine squared. Asexual reproduction, okay? There never was a mother. Asexual reproduction. Divide everything through by cosine squared. All the way through, all three sides, or all three terms. Let's simplify. What is cosine squared over cosine squared? Anything divided by itself is 1. Yeah. Look at this. By the ratio identity, what is sine squared over cosine squared? Tangent squared. Tangent squared. Tangent squared. And then on the right side, by the reciprocal identity, what is 1 over cosine squared? Secant squared. Oh! Who do we have right here? Baby PID number 1. He's a direct result from Papa PID when you divide through by cosine squared. He shows up so often, though, that you don't want to give birth to him every time you need him. Okay? So you do want to just memorize 1 plus tangent squared is secant squared. You can relate secant squared to tangent squared and vice versa. Okay? Got it? Good. The last one, baby PID number 2, is 1 plus cotangent squared equaling cosecant squared. And of course, you can manipulate this as well. You could say cosecant squared minus cotangent squared is 1. Or you could solve for cotangent squared. Cotangent squared is cosecant squared minus 1. You can manipulate it. Now, why is this guy baby PID number 1? First of all, let me show you how you can memorize it. Papa PID was not very good at naming his babies. So once he struggled and came up with this, 1 plus tangent squared is secant squared. The second name of his baby, you can learn by simply adding the word co in front of both of those. Okay? 1 plus cotangent squared equals cosecant squared. And that's baby PID number 2. 1 plus cotangent squared equals cosecant squared. So if you know baby PID number 1, baby PID number 2 is easy, right? It's that second child syndrome. It's like, how come there's no pictures of me growing up, but the older sibling has videos and frames on the wall of him? It's like, well, parenting gets old by the second child, right? The novelty wears off. Sorry, Jenna. Wait till there's 5? Yeah, gosh. Your younger brother probably doesn't even exist, right? Yeah. Is he the youngest? You're yeah, the one. Okay. All right. So anyway, why is he baby PID number 2? Not only does he have the baby name, but now by, again, asexual reproduction. I don't want to get into sex in here. Asexual, okay, reproduction. If we divide everything through now, not by cosine squared, but by the other term, sine squared. Every term. What happens to the first term by the ratio identity? What's cosine squared over sine squared? Cotangent squared. Good. Sine squared over sine squared is 1. And by the reciprocal identity, what's 1 over sine squared? Cosecant squared. And of course, if you commute the two terms in the front because they're both positive, you get 1 plus cotangent squared is cosecant squared. So that's baby PID number 2. He comes from dividing through by the other term. All right? So that's why they're babies. They are direct offsprings of Papa PID. That's Papa with 2 P's. PID standing for Pythagorean Identity, the PIDs. So these are new. You do have to commit these to memory. The other two sets that we've learned, the reciprocal and the ratio, you've already known. Okay? Now, let's see why they're called Pythagorean identities. Example 3. Use the definitions to prove Papa PID. All right, we're going to prove Papa PID. Now, notice I'm using X for the angle here. That's an arbitrary letter. It could be theta, it could be omicron, whatever. We're just going to leave it as X. It represents an angle. We're going to draw a line down the middle here. And let's see. Do you want to start on the right side and somehow build up a 1? Yeah, left. Right. Let's tear that down. Y'all are late again. Okay, I know, right? Oh, man. Okay, let's tear that down. Yeah, all right. Okay, y'all are getting better. Now, the first thing I want to do is rewrite cosine squared plus sine squared. What are we actually squaring? The x, the s and the n, the angle, the ratio. When we write cosine squared of x, that's the condensed way of writing cosine of x quantity squared. We're squaring the ratio. Okay, so whenever you want to use something, it's like a zipped file versus an unzipped file, compressed versus uncompressed. If you want to read the file, you got to uncompress the file. This is the expanded version. So that's what I want to do. So I'm going to call cosine squared of x cosine of x quantity squared, and then sine squared of x sine of x quantity squared. And the reason would be property of notation or whatever. All right, so now, because this is a fundamental identity, we're going to replace cosine and sine with their definitions in terms of x, y, and r. What is cosine's definition? X over r. Now notice we're using x again. It's the same symbol, but it's an entirely different context. The x behind the cosine is an arbitrary angle. The x in the definition is the horizontal position at that angle. Okay? Plus, sine's definition is y over r. Okay, cool. So that's kind of like an identity replacement. Now remember, the other side is your target. So here's a strategy that you can kind of employ. If you notice, the number 1 is not just tall and slender. It is a single term, right? The right side has a single term. One term. No plus or minus. On the left side, we have one term, two terms. So your strategy should be, gosh, I need to get two terms into a single term. And I have fractions. In order to do that, in order to combine two fractions into one fraction, you need a common denominator. So there's your goal. Now, there is some obvious math we can do first. X over r quantity squared is x squared r squared, square the top and the bottom factor, plus y squared over r squared. That would be property of exponents. X over r times x over r, y over r times y over r. So now this looks a little bit better. There's no parentheses. We need a common denominator to add fractions. Do we have a common denominator? We have a common denominator. How lovely. So that's going to all be over the common denominator, bless you. And we just add up, bless you. And then we just add, bless you, the terms in the numerator. I never know what the limit is, you know. Someone keeps sneezing. When do you stop saying bless you and just start saying shut the heck up? Right? Yeah, I would never say that, but you know what I mean. Like, go to the doctor, you know, whatever. Yeah. No, just kidding. Bless you, bless you, bless you. Just like here. Let me just do this, and then you're good for the rest of the day. Okay. All right. Now we have successfully gotten two terms into one term, successfully. But now we need to show that x squared plus y squared over r squared is equal to 1. And we can't just do this. Oh, that's 1. Right? Because now it's like, hey, wait a minute. How'd you go from here to here? And they're like, magic. Right? Yeah, I would count off right there. You would lose so many points right there because you did not lead me to the water. You just said, come this way, come this way. Okay, the water's over there. Like, what? I'm thirsty. Take me to the water. Right? And then salt my oats to make me drink. Like, what, are you a horse? Yes. Any help? Any idea Gosh, what can we do? What? Oh, so what?
Pythagorean theorem.
Pythagorean theorem. This is, after all, called the Pythagorean identity. That's what the P in PID stands for. Let's remember what it is we're doing. Y'all remember the unit circle? Yeah, kind of. Yeah. Oh, yeah, that's a circle with units. That's it. Remember, we have an arbitrary angle. Boom. Right there, then, we stop. We have an ordered pair on the circumference of the circle. We drop a perp. Boom, boom. This is the radius of the circle. This then becomes the x coordinate, which is the horizontal length. That's the y coordinate, which is the vertical length. And we have all three sides of what kind of triangle? A right triangle, by which we can relate by the what theorem? Pythagorean theorem, which tells us then that x squared plus y squared equals OMG. Oh. What is x squared plus y squared equal to? R squared. So I can now make a replacement, a substitution in my numerator with r squared. And the bottom is still r squared. And now you're like, oh yeah, what's r squared divided by r squared? What happens to the r squareds? They divide out to give us 1. And does 1 equal 1? Yes. Oh yeah. Oh yeah. Yes. Is that ooh yeah or oh yeah? Ooh. Ooh. How do you spell oh yeah? Just O-H-H? Oh, more H's than O's. Okay. Oh, there you go. Thank you. Is there a comma in between there? How about instead of a comma, let's put ellipsis points, right? Oh, yeah. Okay. Hey, why is it called the Pythagorean identity? Pythagoras. It uses the Pythagorean theorem, which was actually a contribution of the sect that he was the leader of, not necessarily the one guy. His idea was don't eat beans. His people were like, hey, the sum of the square of the two short sides of a right triangle equal the square of the third. And he's like, oh, okay, let's go kill Hypasus. Right? Remember that? Remember that? Yeah, murderer, Pythagoras, the murderer, Pythagorean. Okay, now it should not be that of much of a revelation to you because on the unit circle, it's a unit circle because the radius is 1, which means on the unit circle, the x is in fact the cosine of this angle theta, and the y is the sine. And so, by the Pythagorean theorem, x squared plus y squared equals r squared, cosine squared plus sine squared equals 1 squared. Ta-da! Pythagorean theorem. That is Papa PID, because that is directly the Pythagorean theorem that you've memorized. A squared plus b squared equals c squared. The other two in a slightly different form. Those are the offspring. Those are the babies. But that is Papa PID. Pretty magical. Papa PID is pretty cool. We use them a lot. Papa PID. Okay, now you're hungry for pizza. Or someone last period said, that sounds like Peppa Pig. And I'm like, yep. So, yeah. Peppa Pig, I guess, is a show y'all grew up watching. Yeah. No? I've seen it once or twice. Okay. It's a little bit better than Caillou. Caillou kind of creeped me out. But Peppa Pig, not a big fan. But if you want to call it Peppa Pig instead of Papa Pig, that might work, you know. I volunteered last period that maybe Papa Pig, a single father, and Peppa Pig, a single female, might find love, you know, and establish a sound relationship and eventually have more offspring in which in the future there might be more baby pigs to memorize for future Precal students if we get Peppa Pig involved. And when I mentioned that, someone last period said, all right, I'm done learning for the day. I'm out. I'm like, why? You know, I don't understand where all this stuff comes from. I'm like, I'm sorry. Okay. He said he liked the class, but he was done for the day. Yeah. So I'm sorry if y'all take me off task and I follow y'all, then It's my responsibility to get y'all back on track. So, all right. What's that?
They were all saying that Peppa Pig is not for my time, but I vividly remember watching it, and it did come out in 2004, so I was right.
Yeah, no, it was. It was because I mean, I watched it with my two offspring. Yeah. Um, okay, so we have three sets of identities: reciprocal, ratio, and the PIDs. And the PIDs are the only new ones that you have to memorize. And you have to memorize them like the back of your hand. Like if you saw the back of your hand in a lineup, first of all, it's the back of your hand. Which side's the back? Does it depend which way you're facing? I think the back of your hand is probably the knuckle side, right? Not the palm side. That's what I'm thinking. So could you spot the back of your hand in a lineup? Like, oh, there's the back of my hand. Could you? So there's that whole idiom that says, hey, I know it like the back of my hand. It's like, why do you know the back of your hand so well, right? Right? But anyway, you should know these PIDs, quote unquote, like the back of your hand, if you know the back of your hand well, because you don't just need to like be able to say 1 plus cotangent squared is cosecant squared. What you need to be able to do is when we're working through a theorem, you have to be like, oh yeah, that is in my mental catalog. I know that this is a possibility of something I can use. And if you don't have it memorized that well, it's not going to be in your mental catalog. Okay? In other words, you're going to have to say, I can write cosecant squared in terms of cotangent squared. And that's the tool that I need to use right here. If you don't have it memorized, you're like, what? When's the retest? Okay? You don't want to do that. So stay ahead of the game, commit it to memory, and then practice, practice, practice. Got it? Okay, good. Let's look at another set. Hey, guess what? You already know these. You already know these. These are the even-odd identities. Every one of the trig functions has some type of symmetry. Remember? Yes, 4 of them were odd, 2 of them were even. Which 2 were even? Cosine and secant. It's reciprocal. Okay? Cosine and secant are the only 2 evens. And if you need help remembering that, secant spelled backward is kes, which sounds like cosine. So cosine and secant, which is cosine backwards, are even. If you need help relating things, okay? Those are the only 2 that are even, meaning the other 4 are odd. Yes, the other 4 are odd. So here you go. Here's your first pair of odd functions. Sine and cosecant are both odd. I paired them as reciprocals. Now remember the algebraic consequence is negative inputs can become negative outputs. You can bring them out front. Or versa versa, really. We've always brought the negative input to the outside to make it easier to graph, but hey, maybe we want to bring a negative on the outside back to the inside. Maybe, right? We could do that. Negative inputs or negative outputs. The other set are tangent and cotangent. Those are the other 2 pairs of odd functions. So again, negative inputs become negative outputs, or negative outputs become negative inputs. And then the classy ones over here, the even functions, secant, its reciprocal, cosine. What happens when we have a negative input on an even function? We forget about them. Fat. Yeah, forget about them. Forget about them. Gangsters don't pronounce the TH, right? They just use the like rec. Forget about them. You don't have like an enunciating mafia guy like, forget about them. Right? I'm going to make them an offer they can't refuse. Okay. You sound like a great salesman. The negative inputs go away. Okay? So you already know those. You already know those. So we have reciprocals that you already know, ratios that you already know, even odds that you already know, and then the PIDs, which are awesome, which you want to know. Okay? Now there's only one more set of fundamental identities. You ready for them? Yes. They are called co-function identities. And guess what? You already know these. You do. You already know these. Right? I've been stressing from day one what the co in cosine, cotangent, cosecant means. It means what? No, not coterminal. Complementary. Órale, seguro. Complementary. Complementary. Okay? Complementary means that two angles add up to what? 90 degrees. So if I have an angle theta equals 20 degrees, what is the complement of that angle? 70. How'd you get 70, Mikey? I'm just curious.
Oh, because 20 plus 70 is...
So you just 70 just popped into your head and you knew it?
90 minus...
Oh, okay, there you go. Metacognitive strategies. You knew that it was the difference from 90 there, and then you knew that was 70, and then you checked in your head by adding them back together. But you just did all of that in just a flash. It's great, right? If I have an angle, then its complement is 90 minus that angle, and that's in degrees. So in general, if theta equals x degrees, the complement is going to be 90 degrees or minus what? X, right? In general. What would it be in radians? If I have an angle like pi thirds, what would the complement of pi thirds be? Not 90 minus, but what? Pi halves. Why pi halves? It's equivalent to 90 degrees. It's pi halves minus pi thirds, which of course y'all know is pi sixth. Good. Someone last period said, I don't know. Okay. You can do your crisscross applesauce, right? You take your first diagonal product down that way from top left to bottom right in that order. That's 3 pi minus the other diagonal is 2 pi. 3 pi minus 2 pi is 1 pi. That's your new numerator times the product of the bottom is 6. That works well, the crisscross applesauce butterfly multiply method that we talked about. Okay? That works well when your two denominators are what? They only have what in common? Factors of 1. We call those when their LCM is their product, they only have common factors of 1. They are another co-word, not coterminal, no, not cotangent. There's a lot of co-words. Cooperate, no, not cooperate. Cohabitation, no. Co-prime. Remember that word, co-prime? You got to go back to like September, like 2018. Co-prime. Remember that? Co-prime. Co-prime. If two numbers are co-prime, their LCM is their product. So we get pi 6. Now, let's do it in general. If I have an angle in radians that's x, its complement is going to be what? Pi halves minus x. Always pi halves minus x. Always. Never not pi halves minus x. Right? Mikey showed us that when he came up with 20 so magically. Right? Yeah. Always pi halves minus x. So, here we go. The last ones. Sine and cosine are complements of each other. So sine of an angle x is its complementary function of the complementary angle of x, which is pi halves minus x. Now they're co-functions of each other, so it works the other way around. Cosine of a given angle x is equal to its complementary function sine of the complementary angle of x, which is pi halves minus x. Always pi halves minus x, okay? So how do you get the co-function? Well, if there's not a co in the word, you add the word co. Sine, add co, get cosine. If there is a co in the word, cosine, take co away and you get sine. That's how you get co-functions. So what are the other two pairs? Tangent and cotangent. So tangent of an angle x is equal to cotangent of its complement. Cotangent of x is equal to the tangent of the complement. And then quickly the last two, secant and cosecant. It works the exact same way. You already know these, but you haven't seen them quite in this format. But you already know these. So I want you to tonight go through here, drill yourself. There are Quizlets. If you go to Corpy's World, the bell is going to ring soon. Go to Corpy's World and just look up 6.1. There's fundamental identity flashcards. Okay? So help yourself, and we'll see you tomorrow. Have a great rest of your today. Remember, it's the